Hello, in this video we're going to talk about the fundamental theorems of calculus. In the first video we're going to go over the first fundamental theorem, and then I'm going to create a second one for second fundamental theorem of calculus. Remember that when you wanted to find integrals in single variable calculus, the way you did that was not really following the Archimedean sequence of partitions. If you want to find integrals using Archimedean sequence of partitions, you will have to first show that a sequence of partitions is Archimedean. And even assuming that, you will have to find the upper sums or lower sums and then take the limit. Finding the upper sums when functions get more complicated is quite difficult. Because of that, we are looking for a tool that allows us to find integrals without having to go through the process of finding a sequence of Archimedean sequence of partitions and then finding the upper sums and then taking the limit, because that process is challenging. The way you evaluate integrals in single variable calculus is, let's say you want to find the integral from a to b of x cubed dx. The way you did that was you found an antiderivative, in this case x to the fourth over 4, and then you evaluate at the endpoints. You plug in the endpoints and then you subtract. We would like to prove this statement is in fact valid. So first, a notation. Instead of writing down integral from a to b of f, we sometimes write down integral from a to b of f of x dx to make it clear what is our independent variable x. So theorem 7.10, it is called the first fundamental theorem. In some textbooks they call it fundamental theorem part A, fundamental theorem part B. In this book we call it, in this class we call it the first fundamental theorem. Let f from closed interval ab to r be continuous over ab and differentiable over the open interval ab. Suppose f prime is bounded and continuous. Then the integral from a to b of f prime is f of b minus f of a. Okay, so let's go over the proof of this one. Before we prove this, sometimes, and in fact almost all the time, what we do is we show that f prime is continuous over an interval that contains closed interval ab. So for example, your function could be differentiable, continuously differentiable over the entire real line. Then you don't have to check separately that it is bounded and continuous, because by EVT it is automatically going to be bounded. And the second condition is, the second remark is that the conditions of the theorem can be made a little bit weaker. Instead of saying it is continuous, f prime is continuous, we can just say it is integrable over every interval inside AB. And that's enough. But for all practical purposes, in none of our examples we use the weaker condition in remark 7.2. Okay, but in any case, it would be good to know that in fact the condition could be made weaker. What we want to do is to show that f prime is integrable. We know f prime is integrable because f prime is continuous and bounded. So what we're going to do is, so let's note that since f prime is bounded and continuous, it is integrable over the interval a to b. So let's write down an upper sum of f prime. Let P be a partition of AB. Then the upper sum of f prime with respect to P becomes the sum mi of f prime multiplied by I equals 1 to n. So that's the supremum of f prime over the interval from xi minus 1 to xi times this. Now, if you look at the supremum, the supremum is not necessarily a functional value. However, in this case, because it's a continuous function, it is a functional value. I'm going to avoid using that because there's two issues. First, at the endpoints, there is a problem. F prime is not defined at A or at B. And second, I'm actually going to be able to prove it without continuity and only using integrability in remark 7.2. Okay, so now notice this. Notice what happens if you look at if you apply the mean value theorem. So f of xi minus f of xi minus 1 over xi minus xi minus 1 is equal to f prime of some ci for some ci between xi minus 1 and xi by the mean value theorem. So this means since mi is the supremum, f of xi minus f of xi minus 1 over xi minus xi minus 1 is going to be less than or equal to the supremum, which is capital Mi. Now, if you cross multiply, you get f of xi minus f of xi minus 1. So multiply both sides by xi minus xi minus 1. Mi of f prime xi minus xi minus 1. Now sum this up and you get sum I equals 1 to n f of xi minus f of xi minus 1. That is the left side. And the right side is just the upper sum for function f prime. Now this is a telescoping sum. This guy is a telescoping sum. So that's f of b minus f of a. That is less than or equal to the upper sum. Okay. Since f of b minus f of a is less than or equal to all upper sums, infimum of the upper sums is integral. So f of b minus f of a would be less than or equal to the integral from a to b of f prime. Because integral is the infimum of all the upper sums. And f of b minus f of a is a lower bound of upper sums. Infimum is the largest lower bound. Now similarly, f of xi minus f of xi minus 1 over xi minus xi minus 1. This is a functional value for f prime by mean value theorem. Therefore, this is greater than or equal to the lowercase mi for f prime. And if you do the same thing, you will get f of b minus f of a. So multiply by xi minus 1 and add it up is going to be greater than or equal to the lower sum of f prime p. Again, notice that supremum of the lower sums is integral. So this gives you f of b minus f of a is greater than or equal to the integral from a to b of f prime. So integral of f prime from a to b is greater than or equal to f of b minus f of a. So this is 1. And also less than or equal to f of b minus f of a. So that means it must be equal. 1 and 2 imply integral from a to b of f prime is equal to f of b minus f of a, which completes the proof. Okay, so notice that I didn't actually use the fact that f prime is continuous. I used the fact that f prime is integrable inside the interval because I wanted to show that f prime is integrable over the entire interval from a to b. Okay, so this theorem is a theorem that we used a lot in evaluating integrals. You find an antiderivative and then you evaluate it at the endpoints. Okay, so now because of the importance of this, we are going to name this antiderivatives. We're going to name the function whose derivative is a given function an antiderivative. So let f from ab to r be a function that is continuous and bounded over of open interval a to b. So it's continuous and bounded over the open interval. We say a continuous function f from closed interval to a closed interval ab to r is an antiderivative of f if f prime of x is equal to capital F prime of x is equal to lowercase f of x for all x in ab. So lowercase f may not be continuous over the closed interval. Lowercase f must be continuous over the open interval. Okay. We are going to use the fundamental theorem that we just proved, first fundamental theorem, to evaluate these integrals. So the first one, if you look at x to the r, we know an antiderivative of that. So x to the power of r plus 1 over r plus 1 is differentiable, is in fact continuously differentiable, is c1 over the entire real line. And its derivative is just x to the r. So thus, integral from a to b of x to the r is going to be, you evaluate this function at b to the r plus 1 over r plus 1, and then subtract the value of this function at a. So that is b to the r plus 1 minus a to the r plus 1 over r plus 1. Okay, let's look at the second one. F of x is 2x when x is between 0 and 1, and it is x cubed when x is between 1 and 2. So note that f of x is bounded. The largest value is 8. So f is bounded. Also, f is continuous over both 0, 1 and 1, 2. So by a theorem, f is integrable over both of these intervals, over 0, 1 and 1, 2. By an exercise, it would be integrable from 0 to 2. By an exercise, f is integrable over 0, 2, and by additivity, integral from 0 to 2 is equal to integral from 0 to 1 plus integral from 1 to 2. Okay, so by a theorem, since integral does not depend on the endpoints, integral of f becomes integral of x, because, or was it 2x? Yeah, 2x. And same thing for the other one. It is x cubed. But this is equal to twice integral from 0 to 1 of x. And we already found this one. This is 1 squared minus 0 squared over 2. So that's 1. And this one is 3 to the 4 minus 1 to the 4 over 4. So that is 81 minus 1, that's 80 over 4. And that is 20. So that means integral from 0 to 2 is 21, which is exactly what we wanted to find. Okay, so if you would like to continue with the subject of advanced calculus, feel free to subscribe, and I will see you in the next video.